do a small drilling operation we have to do. So the prerequisite is that drilling we are going to do outside, because to balance the line. Otherwise, if we have to do the drilling also on the same integrated line, other product will be waiting. There will be jamming of stations. So that is one simple example. I'm going to take you to the line balancing. Okay, line balancing, and whichever the machine is taking the maximum amount of time, and which machine is taking the minimum amount of time, and what is the storage buffer we have to provide. All this will be the method, the meaning of line balancing. The processing technology is that the processing technology, I am going to do a heat treatment operation. I have my heat treatment plant at my site. So heat treatment is that blindly, please don't believe that all the metal simply we can do the heat treatment. Heat treatment and annealing. Heat treatment is we are going to do a hard coating, and we are going to do the hardening of the material to the core or to a certain thickness. That is the hardening. And annealing is that we are going to relieve the heat treatment so that we can go for the machining. And to do this, at least basically to open my factory or open my industry of the heat treatment and annealing, and I should have a basic understanding and knowledge of the metallurgy and the material list. So what kind of material and what is the composition of the material, and based on this, what is the treatment I can able to give, and what is the thickness of heat treatment I can do, and what is the duration it is required, and what is the metallurgical microstructure which is required, and what was earlier. So these are the basic requirement. The processing technology, it is called a processing technology, also will be helping you for the transfer lines. Very simple in sheet metal operations, a hardened steel sheets or CRCS steel, cold rolled carbon steel sheets, and the galvanized sheets and the stainless steel sheets, and all these will be having different microstructure, and their capability of deformation will be different. That the machine, what kind of operations we have to do, that has to be understood by the person or engineer in order to use it. So these are all the basic requirement. Those are called processing technology. And the system reliability, and how much we can reliably depend on the system. How much reliably we can depend on the system, that we will be discussing. Okay, the analysis of transfer line under this line balancing, processing technology, and system reliability. Now let me get into a depth of line balancing. It is most closely associated with manual assembly line, but it is also an issue on automated production line. So somehow the total work content to be accomplished on the automated line must be divided as evenly as possible among the workstations. The meaning is that divided possibly into number of at different workstations. Just now I told a threading operations I want to do. So before you go to a threading operation, a prerequisite is that at the end of the rods, I have to create a work centers. That is, we have to do the drilling, okay, to hold the job. So that means we are going to evenly distribute the works. So final finishing work can be done on the flow line. Okay, in a manual assembly line, the total work content can be divided into much smaller work element, and the element can be grouped and assigned to workstation to determine the task as it is performed at each station. The meaning here I have given, you can see that the example is machining transfer line. Certain operation must be performed before others. Drilling must be proceed. We have to do the drilling and tapping to create a threading hole. So that means, I hope you understood, all these operations you are going to do by keeping the plate in front of you. You are going to do prepare the food. It is not correct. Prepare the food. Once the food is ready, keep the plate in the similar way. The amount of time which has sequentially taken on a particular station will be reduced if you are going to reduce the number of operations. So that is what the line balancing. Okay, line balancing. And the next is processing technology. Refers to the body of knowledge about a particular manufacturing process used in the production line. Just I had given an example here. The one should have to understand if he has to have some machining operations, if he want to do on a material, he should have a small basic idea about metallurgy and machinability. And if he is going for the lathe operation, CNC machine operation is not like your the normal lathe operation. Each and every tooling is very costlier. So for this particular type of work, for this particular speed, what kind of tool should be used? So, and what should be the operation parameters, how those can be optimized, speed, feed, and depth of cut. So all these will be possible to understand. And one of my friend has done a PhD on the machining parameter optimization on a CNC machine. Speed, feed, and depth of cut, how we can maintain, we can optimize them in order to increase the tool life and machine life and maximization of the efficiency of the system. So all these will be possible once you have a small basic idea about the metallurgy and machinability. Okay, this is one example. The second example I had taken is very simple example earlier. This I have not given here. The hardening, the heat treatment and annealing industry, they should have the idea about the metallurgy, microscopic structure of the materials and the different type of materials and their composition. Then only they can have the idea about go for the heat treatment. So this is what the process technology. And what is the reliability? The third problem area in the analysis and design of automated production line is reliability. In a highly complex and integrated system such as automated production line, failure of any one component can stop entire system. This reliability problem is primarily focused on this section. So that means to say, so in some other cases, with no internal storage buffer, if you are going to use, so that time, how reliably the machine is working. Based on that, we can frequently one machine is stopping in 1 or 2 times. In 2 to 3 shifts, once one workstation is stopping, there is a failure. So due to this, what happens? The breakdown happens if there is no buffer storage between the 2 workstations. The entire the workstation will be hampered. So in order to avoid this, we should have to have basic idea about the reliability of our plant. Okay, so to have the reliability of the plant, some basic assumptions we will be doing. The workstation performing process operations such as machining, not assembly. So here, to do the basic derivation, or we are not going to do any kind of derivations, to analyze this the automated flow lines, we simply it is performing the machining operation, not assembly operation. The processing time at each station is constant. Definitely it is not correct. The second statement, the processing time at different stations, workstations will be different. But here no, but also what we are going to do is we are going to assume that the workstation N1 to N have the similar amount of time they are consuming. Okay, and work part transfer is synchronous. So already we understood synchronous, asynchronous, and the discontinuous. Okay, the synchronous in the sense the work part are moving by integrated conveyors uniformly. So these are the 3 basic assumptions we are going to do. We are going to use in order to do the analysis of flow lines. The first one, they are going to do the machining, not the other assembly operations. The processing time for all the workstations will be same, and the work transport happens by the sync. And we are not going to do, or we are not going to build any mathematical models. We are going to understand these. Now, here the problems will come. Try to remember, one problem will come for the 8 marks in the examination. Cycle time analysis. So what is the ideal cycle time? I am not going to explain anything here. Here you can easily understand. The TC is equal to maximum TSI plus TR. The cycle time, which includes the time which the work part is taken from for to move from the conveyor to the machine, and the total time will be idle time. Okay, it is the TC. It is the cycle time. Okay, or idle time. And TSI, it is the processing at station. Ith station. TS, it is the processing at the station. Here I have given I number of stations, 1, 2, 3, 4 to the ith station, and TSI is the processing of ith station, and TR is repositioning time, and this is called as the transfer time. Okay, and maximum TSI have been taken because the longest service time have to be taken into account in the production line. Okay, so whichever the machine is taking the maximum amount of time, that time will be considered for the TS. Okay, please, these are around, I think altogether not more than 20 equations will be there. Those you have to write and make a practice. TC is equal to maximum TSI plus TR. TC is equal to cycle time, that is equal to maximum processing time, max TSI plus the TR. It is the repositioning time. Okay, and the next one TP, and you can just self-explanatory. You can go through whatever I have given, and TP is the production time. Production time is equal to TP is equal to TC plus FTD. And here what is this TD? It is the average downtime. Average downtime, and TC is the cycle time. TC is the cycle time, and TD and F is the frequency of failure and frequency of downtime or frequency of failure. Okay, you understood cycle time, downtime, and the production time, cycle time. So TP is equal to TC plus FTD, and the frequency of failure, it happens in approximately 100 cycles, in 100 cycles, in a 50 cycles. So that will be taken, the possible probability of failure is the stoppage of per cycle, that will be taken. For example, in 100 cycle, one time the stoppage happen, that particular the downtime will be divided into 100 cycles, 1 by 100. Okay, that is the TP. And why? What are the reasons here? The beginning only I have given. Here I have given in the operation of transfer line, random breakdowns and the planned stoppage causes downtime in the line. The common reasons are, these are the common reasons: mechanical failure of workstation, mechanical failure of transfer lines, and tool failure at workstation, tool adjustment at the workstation, scheduled tool change at the station, electrical malfunctioning, power outage, and stock out of starting work unit, and insufficient space for the completed part, and preventive maintenance on the line, worker breaks, and poor quality starting work part. So there may be many reasons, and among them these may be the reasons. So due to this, the downtime occurs. That is what I have given here, downtime. Okay, that is what the downtime I have given here. You can go through it. And what is the downtime work? And the expected frequency of line stop per cycle. Expected frequency of line stop per cycle, F is equal to sigma n I is equal to 1 to n pi, and pi is the probability or frequency of failure at station I. Okay, suppose the I is equal to 2, a second workstation I am going to take, P2 indicates the probability or frequency of failure at station 2. Okay, so try to remember this. F is equal to sigma I is equal to 1 to n pi. And now all these, what is this P and all these I have given. Now what is F is equal to NP. F is equal to NP. F is equal to NP. N is the number of stations. P is probability of failure at a particular station. And the performance measurement. The performance measurement are the production rate, Already we know the production rate is equal to 1 by TP, production time, and actual cycle time is equal to 1 by TC. RP is equal to 1 by TP. RC is equal to 1 by TC. Already we have studied this in the previous sections. Now, the idea behind line balancing is that I am going to find out the downtime and the line efficiency. And the downtime plus line efficiency should be equal to 100. Sir, class mugsಕೊಂಡು ಮಾತಾಡಲಾ? Okay, so suppose the efficiency is 95%, under 5% downtime. So efficiency plus downtime is equal to 100%. So the line efficiency is equal to TC by TP. TC is what? Already we know that RP is equal to 1 by RC is equal to 1 by TC, and TP is we can obtain from RP is equal to 1 by TP, and this efficiency E is equal to TC divided by TC plus FTD. So TP is equal to TC plus FTD, already we know. So this we are going to I have substituted. TP is equal to TC plus FTD. Okay. And what is the downtime? Downtime can be calculated by this equation. Okay. The downtime can be calculated by this equation. Then E plus D is equal to 100%. Now, cost per unit. These are all the equations you'll be using. Here it is not a derivation. Please don't. I have given an explanation there. What is the cost per unit? The cost per unit is CM plus C0 TP plus CT. And what is the CM is the cost of material. And C0 is cost per minute to operate the line. And TP is the average production time per piece. And CT is equal to the cost of the tooling per piece. So many other costs also can be included in this. For example, cost of downtime, the cost of the raw material, and the cost of the waste product. All these will be giving you the cost per price. Okay. So CPC is equal to CM plus C0 TP plus CT. Okay. This is what the equation. And here I have a small problem, and you can go through it. A machine tool builder submit a proposal of 20 stations. I is equal to 20 station transfer line to machine a certain component currently produced by conventional method. The proposal states that the line will operate at a production rate of 50 pieces per hour. So production rate 50 pieces per hour at 100% efficiency. On a similar transfer line, the probability of station breakdown per cycle is equal to 0.005 breakdown per cycle. It is also estimated that the average downtime per stop will be 8 minutes. The starting cost that has to be taken for the machining is 3 rupees per part. The line operates at a cost of 75 rupees per hour. The 20 cutting tools. Okay, so that means we'll be using last for 50 parts each. So that means we are going to use 20 cutting tools, and the average cost per tool is 2 rupees per cutting edge. And find production rate, line efficiency, cost per product, the production of piece on the line. And here I have calculated. It is self-explanatory. You can go through it if you want. I can explain it later on. TC is equal to 1 by RC, and F is breakdown time. And here I did a small mistake. It has to be within a bracket. That I'll rewrite and send it to you. And TP is equal to TC plus FTD. Submit to those. And RP is equal to 1 by TP. That also is submit. Then I can able to calculate the production cost per piece. I can able to calculate.